Hello, welcome to a new physics lesson. Today we are going to find the D'Alembert's formula that is going to be a solution for the one-dimensional wave equation. In this particular case, we are going to apply it to the case of a string that is moving due to an external force. Okay, so that string can be thought to be in tension, right? So that when you apply a force in any of the points of the strings, well, it will start to oscillate. And then we are going to describe the motion of the string with a displacement function u of x comma t, right? So this function is going to depend on the position and the time, right? So for example, we will have this kind of motion that for any point of the string, we will have some value of displacement with respect to the x-axis. So the goal here is going to be to find that function u of x comma t that is going to describe the motion of the string. Okay, so on a previous lesson, we showed that this string moving satisfies the wave equation. The second derivative of u with respect to time equals a squared, and the second derivative of u with respect to x, where a can be seen as the tension applied to the string divided by the linear density of mass of the string, right? Okay, perfect. So now we are interested in finding a solution for this differential equation. So to find a solution for this equation, we are going to propose that u, which is a function of x and the time, will now be a function of a variable p and q, right? Where p and q are going to be functions of x and t. So this will take the shape of u of p of x comma t and then q of x comma t. Okay, so we are going to calculate these derivatives for this new u, but in terms of p and q. And the functional relation between p and x and t and q and x and t is going to be the next. P equals x minus at and q equals x plus at. So this is just a change of variable. And then to express the derivatives of u with respect to x and with respect to time in terms of p and q. So to do that, we are going to calculate, well, the derivatives by using the chain rule, right? So this is going to be the derivative of u with respect to x is the derivative of u with respect to p times the derivative of p with respect to x. But u is a function of p and q, so this is going to be the derivative of u with respect to q and the derivative of q with respect to x. So this is the derivative of u with respect to p and the derivative of p with respect to x, but that is just 1, right? Just by looking to this expression. And then plus the derivative of u with respect to q, and then again 1 because the derivative of q with respect to x is just 1. Perfect. So what is going to be the second derivative of u with respect to x? This is just the derivative with respect to x of the derivative of u with respect to p plus the derivative of u with respect to q. So this is the derivative with respect to p of the derivative of u with respect to p times the derivative of p with respect to x. And now we are going to do it, but with the variable q, right? So this is the derivative with respect to q of the derivative of u with respect to p, and then times the derivative of q with respect to x. Okay, so this was for the first element of the sum. So now we have here the derivative with respect to p of the derivative of u with respect to q, and then the derivative of p with respect to x plus the derivative with respect to q of the derivative of u with respect to q, and then the derivative of q with respect to x, right? So as we mentioned, these are just equal to 1. So we are going to have something like this. The second derivative of u with respect to p plus the second derivative of u with respect to p with respect to q and then plus the second derivative of u with respect to p with respect to q plus the second derivative of u with respect to q. We know that, well, the solution to the wave equation is a well-behaved function that allows us to switch the order of the derivatives, right? So that is just a curious fact. We're not going to do it right now, but you should know that in this case, these two quantities are equal, so we could sum these quantities. Perfect. So this was just the second derivative of u with respect to x. So now we need to calculate, well, the second derivative of u with respect to time, right? So the derivative of u with respect to time is going to be, it will be the derivative of u with respect to p times the derivative of p with respect to time plus the derivative of u with respect to q, the derivative of q with respect to time. Okay, so we now have to be careful because the derivative of p with respect to time now is equal to minus a, right? And then the derivative of q with respect to time is equal to a. Okay, so I think that, yeah, this is minus a, this is a. So let me rewrite this as minus a, the derivative of u with respect to p, plus a, and then the derivative of u with respect to q. And now we need to take the second derivative of u with respect to time as the derivative with respect to time of, let me factor that a, so it will be a, the derivative with respect to time of minus the derivative of u with respect to p plus the derivative of u with respect to q. Again, remember that these two quantities are functions of p and q, okay? So we need to use the chain rule again, taking that into account. So this is going to be a times, it will be minus the derivative with respect to p of the derivative of u with respect to p times the derivative of p with respect to time, and then plus the derivative with respect to q of the derivative of u with respect to p times the derivative of q with respect to time. Okay, and then plus the derivative with respect to p of the derivative of u with respect to q, and then the derivative of p with respect to time, and then plus the derivative with respect to q of the derivative of u with respect to q, the derivative of q with respect to time. Okay, perfect. So again, this quantity is equal to minus a, this is equal to a, minus a, and a. Okay, perfect. So what is this going to be? Well, we have an a here, minus times minus is plus, and then, well, we have plus a, the second derivative of u with respect to p, and then plus a, the second derivative of u with respect to q with respect to p, minus a, the second derivative of u with respect to p with respect to q, and then plus a, the second derivative of u with respect to q. And yeah, from here, you see that there is a minus sign for the derivative of u with respect to p, right? So I think that this plus should be a minus, and this should be a minus. To get that this is equal to a squared, the second derivative of u with respect to p, minus and the derivative of u with respect to q with respect to p, and then minus the second derivative of u with respect to p with respect to q, plus the second derivative of u with respect to q. Okay, so this is the second derivative of u with respect to time. Perfect. So getting back to the wave equation, we have that this quantity that we just found has to be equal to a squared that multiplies the second derivative of u with respect to x squared. So we need to set this equal to a squared times the second derivative of u with respect to x, which is this quantity that we have here. So let me copy. Okay, perfect. So this is what we get if we set equal to be the second derivative of u with respect to time and a squared, the second derivative of u with respect to x. Okay, so it's easy to see that this element can cancel with this, and this element can cancel with this. To get that, well, it will be minus a squared, and let me set this together now, to the second derivative of u with respect to q with respect to p, just by switching the order of the derivatives. And this is going to be 2a squared, the second derivative of u with respect to p with respect to q. So with this, it's very easy to see that after making these cancellations, the negative of this derivative is equal to, well, the derivative. So that means that that second derivative has to be equal to 0. Right? Okay, perfect. So I think that this is an equivalent equation for the wave equation, right? Take that into account. This is just like other way to watch the one-dimensional wave equation. Okay, perfect. So what will be a solution for this equation? Well, just by inspection, we see immediately that, for example, u of q comma p is equal to maybe theta 1 of q plus theta 2 of p is a solution for this equation, right? We see easily that the derivative of u with respect to p is equal to just the derivative of theta 2 with respect to p, and then the second derivative of u with respect to q with respect to p, well, it's going to be the derivative with respect to q of a function that is only of the variable p. So that is, well, equal to 0, right? Perfect. So as we can see, we verify that this structure is a solution for the wave equation. But we know, and let me write this as theta 1 of p and theta 2 of q, just because, well, we are taking as our first variable the p, right? Just let me remind that p was defined to be equal to x minus at, right? If you remember at the beginning of the change of variable, we said that p is equal to x minus at and q is equal to x plus at. So that means that our solution for the wave equation in terms of x and t is equal to theta 1 of x minus at and the plus theta 2 of x plus at. So I think this is a very familiar topic in general physics, like in vibrations or wave mechanics, right? You should already know that these kind of functions are actually, well, related to solutions of wave equations, where this element is related to a wave that is moving through the right, and that this wave is related to a wave that is moving to the left, right? But how can we see that? Well, we can think that if a wave is moving to the right, its velocity is equal to plus a, right? Recall that the a variable is the velocity of the wave. So we can see that for a wave moving to the right, the velocity, which is dx dt, is equal to a. But if we integrate this equation, we will get that x is equal to at and then plus a constant. But we can see from here that this constant is equal to x minus at, right? So if we can think of an observer that is moving with the wave with velocity a through the right, well, the value of the function is going to be constant all the time. And the argument of the function is going to be, well, x minus at. So it will be like the theta 1 of c equals to theta 1 of x minus at, which is this element over here that, again, it corresponds to the wave moving through the right, as we mentioned here. So a similar argument can be applied for this function. You will see that this corresponds to a wave that is moving to the left. Perfect. So with this, we are now able to construct what is the D'Alembert's formula. That is going to be a formula that applies for a specific problem named as Cauchy's problem, right? So the Cauchy's problem is just a wave equation problem with some specific initial conditions. So the Cauchy's problem is about finding a solution for the wave equation in just one dimension in this case, where t is greater than 0 and that x is between minus infinity and infinity. Okay? Okay, and what will be the initial conditions? Well, we are going to have, for example, that we are going to have an initial distribution of positions for the string. I mean that, for example, the initial motion of the string can be of this shape, maybe, right? So at time t equals 0, we have an initial distribution of positions that tells us what is the beginning of the motion of the string. So this can be seen as u of x evaluated at t equals 0 equals to some function of x, right? So for any value of x, we have some value of the function u, okay? That is described by this function of x. And then we are going to have another initial condition that is also for t equals 0 that tells us that the derivative of u with respect to time evaluated at x equals 0 is equal to some other function of x. So if we think this function as the initial distribution of positions for the string, we can think of this function as the initial distribution for velocities of the string, right? Okay, perfect. So how are we going to find a solution for this problem? Well, we are going to make use of these initial conditions that define the problem. Okay, so we know that for a one-dimensional wave equation, the solution is u of x comma t equals theta 1 of x minus at plus theta 2 of x plus at. So from here, if we evaluate t at 0, we are going to have that, well, phi 0 of x is equal to theta 1 of x plus theta 2 of x. Okay, now we are going to make use of the second initial condition. So to do that, we need to take the derivative with respect to time of u. But again, well, we have that the argument of theta 1, well, is a function of x and t. So we need to take first the derivative of theta 1 with respect to the argument, and then the derivative of the argument with respect to time, right? So we are going to use this notation. The derivative of u with respect to time is going to be minus a, and then theta 1 prime of x. You should remember that the notation of the derivative prime, it means that you are taking the derivative with respect to the whole argument of the function, right? So that's why I just write x here. And then the derivative with respect to time of the argument is minus a. So that's why I'm multiplying by a here. And then plus a, the theta 2 prime of x. And the initial condition says that, this is equal to some function phi 1 of x. Okay, so we can see this as phi 1 prime of x minus phi 2 prime of x equals to phi 1 of x divided by, or multiplied by my minus 1 divided by a, like this. Okay, so from this equation, what we are going to do now is to introduce a new variable alpha for these equations in the next way. It will be theta 1 prime of alpha minus theta 2 prime of alpha equals minus 1 divided by a phi 1 of alpha. And we are going to take the integral on both sides of the equation just to get back to the variable x that we had before. So we can see this as the integral from 0 to x of theta 1 prime of alpha d alpha minus the integral from 0 to x theta 2 prime of alpha d alpha, and then equals 2 minus 1 divided by a, the integral from 0 to x of phi 1 of alpha d alpha, and then plus some constant of integration, right? So looking that these are derivatives or total derivatives with respect to the variable alpha, we can use the fundamental theorem of calculus in these two elements to get that this is going to be theta 1 of x minus theta 2 of x equals to minus 1 divided by a, the integral from 0 to x of phi 1 of alpha d alpha plus c. Perfect. But we have found that theta 1 of x plus theta 2 of x is equal to phi 0 of x. So let me write that here. Theta 1 of x plus theta 2 of x is equal to phi 0 of x. Okay, so as you can suspect, we are going to subtract and then to sum these two equations to get some results, right? Okay, so if we sum, we are going to get 2 theta 1 of x equals minus 1 divided by a, the integral from 0 to x, phi 1 of alpha d alpha plus c, and then plus phi 0 of x. Perfect. So from here, we can get that theta 1 of x is equal to minus 1 divided by 2a, the integral from 0 to x, phi 1 of alpha d alpha plus c divided by 2 plus phi 0 of x divided by 2. Okay, now if we subtract those equations, let's say this one minus this one, we are going to get 2 theta 2 of x equals phi 0 of x plus 1 divided by a, the integral from 0 to x, phi 1 of alpha d alpha plus c. Now from here, we get that theta 2 of x is equal to phi 0 of x divided by 2 plus 1 divided by 2a, the integral from 0 to x, phi 1 of alpha d alpha plus c divided by 2. Okay, remember that we mentioned that the solution was of the form u equals to theta 1 plus theta 2, and that theta 1 is actually a function that is expressed as a function of x minus at, right? So we need to evaluate these two quantities that we found at x minus at for theta 1 and x plus at for theta 2. Okay, so we are going to have that u of x comma t equals to theta 1 evaluated at x minus at. So that is minus 1 divided by 2a, the integral from 0 to x minus at, phi 1 of alpha d alpha plus c divided by 2 plus phi 0 of x minus at, and then plus theta 2, right? So that is phi 0 of x plus at divided by 2 plus 1 divided by 2a, the integral from 0 to x plus at, phi 1 of alpha d alpha plus c divided by 2. Okay, and just to reorder, and I think that I forgot to divide by 2 this function phi 0, right? Okay, and then we are going to reorder a little bit. We can sum this c divided by 2 plus c divided by 2 to get that u of x comma t is equal to 1/2 phi 0 of x minus at plus phi 0 of x plus at, and then plus 1 divided by 2a. It will be the integral from 0 to x plus at, phi 1 of alpha d alpha, and then minus the integral from 0 to x minus at, phi 1 of alpha d alpha. Okay, and then plus c. Okay, I think that with this, we have found the goal of the video, which is the D'Alembert's formula for the Cauchy problem, right? So this is like a general solution for the Cauchy's problem. Recall that this is just finding the solution for the one-dimensional wave equation, but with these two specific initial conditions. So yeah, I think that this is the important result of the lesson. And just to take into consideration, we could change this minus to a plus, right? So this element will become the integral from 0 to x plus at, and let's add this one divided by 2a factor, the integral of phi 1 of alpha d alpha, and then we could change the order of the limits here to take the plus sign over here. So this will be the integral from x minus at to 0 of phi 1 of alpha d alpha, right? Yeah, this factor over here. And then we can see this as the 1 divided by 2a times the integral from x minus at to x plus at of phi 1 of alpha d alpha, which I think that is a more elegant way to present the D'Alembert's formula, right? Okay. Yep. So I think that with this, I'm going to finish the lesson. And thank you so much for watching.